It did take some time. Okay, so why don't we go ahead and get started then, since we are a little bit behind schedule. I have some introduction slides, but we'll just skip over them. This is our final cyber seminar as part of our virtual workshop on field data management solutions. So today we have Anthony Aufdenkampe from the Stround Center. Next week we actually have our kind of final event, which is the virtual poster session. So we have 8 virtual posters that will be presented, and then 2 vendors, Kissers and My Observatory, are going to give vendor presentations. So it's going to be a really great opportunity to kind of visit a poster session from, the comfort of your own computer screen. So I hope that everyone can attend that presentation, and further details on the poster session will be forthcoming. So just watch your email and watch the Quasi website. So today, Anthony Aufdenkampe is with us to present a path to a data-rich, open-source approach to science. So Anthony is an associate research scientist at the Stround Water Research Center, an adjunct professor at the University of Delaware. He's the co-lead PI of the Christina River Basin CZO and the lead PI of the National CZO Data Integration Project. Anthony was also the recipient of the 2014 Quasi Outstanding Service Award at our biennial over the summer. So Anthony, without further ado, I'm going to hand it over to you. Thank you very much.
Thank you. So thanks for all being here. So I was asked to present in this series, and my first thought was, sure, I'll present all the things that we're doing for our critical zone data project. But it was all about, building cyber infrastructure and tools that we've developed or are in development. But the whole theme to this series seemed to be more about hands-on, how to get people started at really managing data for field observation programs, tools, tricks, and techniques for handling data in the field or recently from the field. So rather than talk about what we're doing for the critical zone observatories, which is also somewhat specific to that program, I thought I would kind of describe my path in going from being an aquatic geochemist to someone who's using some of these tools, and I think I learned a lot of lessons along the way. It's been about a 3 or 4 year path. So here's an outline of my talk and little tips and tricks and encouragement to really bring you and your teams up to speed with computational science and data management. So let's move forward then. Let's see here. I guess I have to use my mouse. So as a geochemist, I was realizing the need early on. There were all sorts of challenges to managing data, right? The types of sampling approaches that we would use required subsampling samples in ways that were really important for interpreting the final results. And you can see here, this is an example from the System for Earth Sample Registration at geosamples.org. That was the first seminar in the series. And what a headache to try and bring all this data together. If you realize that any single one of these subsamples can then be, I really have to use my mouse, I can't use my arrows, can be then fractionated using chemical and physical techniques for a variety of analyses, for which oftentimes the end values, the end variables are identical, but the preparatory method is absolutely critical to understanding actually the context of that data. So when you combine that subsampling scheme with this fractionation and sample preparation scheme, things can get really challenging very fast. And in the last 2 decades, our capabilities to automate sample processing and, of course, data manipulation have, I think, outstripped our community's capabilities to manage that data in an effective way. So we spend more and more time trying to move numbers around in Excel. Of course, there are challenges related to long-term data. At the Stroud Water Research Center, we have data sets going back to 1967, and dealing with these older file formats, terms that have changed, trying to understand the uncertainty of previous methods and what those methods were, and instrumentation and people and everything else is also a real headache. It's hard, even for an institution that has tried its very best to manage these long-term data sets. That's really challenging. So, and then collaboration. How do you keep everyone on the same page? I think we're being faced with that. And the last is a requirement that we're beginning to face more and more, that we need as recipients of public funding. We are now being required, or will very soon be required, to share our data using public repositories and metadata standards that have been developed by the community. And that, at face value, seems sometimes like a monumental hurdle to a lot of us. And people that I talk to when I say this are just like, how can I ever do that? So we all realize that. And so how do we get there from here? Most of us on the phone here are not data scientists. We're earth and environmental and geoscientists. So it's pretty easy to crash and burn and get lost in all the options. But there was a presentation that I and some of you on the phone here who I recognize attended that really opened my mind to how we were going to do this for our Critical Zone Observatory that was just getting started back in 2010. And it was a presentation at a workshop by the Chief Technology Strategist for Red Hat Linux, and he showed basically how the open source community has figured this out. And one of them was that you don't make massive changes overnight, right? This step or waterfall approach that had long been the approach of commercial software. You have to have so many new features in order to entice everybody to buy the next version. And so you develop this plan, and this would be the ideal plan, but of course, really you know that it's going to be something like this to get to these new features. But the reality is that you divert your resources away from what you're doing, and you never get all the features you wanted to. And this is the reality only in the very best case scenarios. In many, many cases, you end up not actually making progress after a huge development effort, or sometimes completely crashing and burning. So what's the approach for us? Here are a few lessons that Helkinson described right afterwards, is that you want to design for evolution, to know that you're never going to have a final product when you're developing software or data systems. They have to constantly evolve. So I think sometimes among scientists there's this idea, and now that I'm kind of have switched hats and I'm actually on the hook to provide cyber infrastructure for scientists, I'm realizing that there are a lot of us out there who feel like, okay, well, tell me what I need to do now so I can just get on with my science and move forward. And unfortunately, the answer is, well, this is what we're doing now, but this is what we're about to do next. And then there's something that's even more exciting around the corner, right? And the software community does that and knows that you have to design for evolution. And I think that all of us need to think about these, what we're doing with data as an evolutionary process. Iterate quickly, go through this develop, share, test, develop cycle in very, very small circles. Focus on immediate value and utility. So do something that will be immediately valuable. So the smallest incremental step is going to produce a result that will move the ball forward, rather than say, oh, I'm putting in this huge investment and it's going to be this great payback down the road. Start small, and then invite different levels of participation. And in the open source community, this means a much bigger thing. But in our kind of groups, our research groups, grad students, postdocs, collaborators, get a couple people together and say, hey, we're going to try and manage our data a little bit better. Let a couple people think about it, try some things out, and then have the rest of the group test it basically and get back to you right away. So I think one of the very first baby steps we can take is to begin to develop master lists of things like specimen or sample codes, sites, sensor IDs, instruments, methods, people, you name it. If you need some information over and over again when you're describing your data, you should use a master list between you and your team. And it can be, there are all sorts of ways to do this. Just a second here. So, so when you develop these master lists, it would be recommended to think about what other master lists are being developed. This is a set of tables out of basically the information that's in the site list used by Quasi-HIS currently. So you can go find out what is the information model behind the people who are doing informatics for my community. You can look this stuff up and say, oh, when Quasi wants to know about a site, this is all the information that's mandatory and optional relevant to that site. Why don't I make my list more or less conform to that? This information model also has relationships to other bits of information, and we'll talk about that in a moment. So there's another really useful baby step, and that is if you're creating these master lists, the purpose of it is so that you spell the site code the same way every time, and you don't have 15 different ways of spelling Station 2 in your data system, like we had at the Stround Center for decades, basically. So the idea kind of stems from both software engineering, this idea of the DRY principle, don't repeat yourself, right? Single, unambiguous, authoritative representation. That's the master list. So if you have this master list, how do you make sure that it is always the authoritative, unambiguous representation? In database management, there's a concept of normalization, and that's the whole foundation of how relational databases work. It's the same idea. Minimize redundancy, take large flat files, large tables, and chop them up into smaller tables, and then define the relationships between them. Absolutely critical. So the concept I'll demonstrate here. If you've got your spreadsheet with all your data in it, say, well, gee, I don't really need to repeat all this information related to pump house, latitude and longitude, because one, there's a source of error. Two, I don't really know what the definitive list is. If I update it, where do I update it in every single record? So you divide that out. You connect these two tables through what's called a foreign key that refers to a primary key in which the information about the latitude and longitude of a station is recorded once, and it's easy to update. Right? So this is the foundation of all relational database systems. And this is why this is an excellent baby step, because you can develop these master lists as spreadsheets in Excel or Google Sheets or whatever. Use lookup functions, which most of us don't use, but are really easy. The syntax is relatively straightforward. You basically say, instead of filling in a value, you say, go look up this value elsewhere. And it fills in the blank for you. And really, we've found that these are the first steps to organizing your data in a relational database. You don't have to know how to manage a relational database to do this. And we started out in Excel because we have all of our data on servers, but we started to, of course, come into the constraints of having multiple people edit in Excel. And now we're actually have this highly linked master list system all in Google Docs that everyone at the Stround Center uses, because we're still institutionally working toward having, the golden master database, which doesn't quite exist yet for a number of reasons. So they're baby steps. So our data will be ready when that great database, which, by the way, is the Observations Model version 2, for those of you who are wondering. When that data system is completely ready, our data will be ready to put into it. So the next baby step is to use control vocabulary. These are terms and the definitions of the terms that are strictly predefined and shared for reuse. So you can have control vocabulary internally. One person on a laptop could create your own. But typically we work in teams, and generally the control vocabularies that are useful are those that are managed by community authority, such as the quasi-HIS team or specific individuals in the team, in fact. But even though the authority manages it, it's still for the community, and input is generally accepted by the community. So these lists, as much as they're controlled, they're also dynamic, and they change, and they're usually placed in locations online that allow machines and people to quickly check what the latest version is. So this is the simplest example, actually, on quasi-HIS of these terms and their definitions, and the ability for any user to go in and suggest an edit, which of course will be reviewed by the authority, but nevertheless, it keeps everyone on the same page, and the authority can say, you know what, that sounds a lot like another term that we have on this list, or that's a great idea. So start using that. The next thing is really to encourage all of us to start using code. I mean, we can do an enormous amount in Excel, but there are limits to what can be done in Excel. And I love this quote from the software carpentry team. My guess is that a good number of you have heard about software carpentry, but I really encourage everyone to get the grad students and themselves and everyone else to dive in and find out what you can do at the command line or with simple bits of code. And this quote basically says it all. You know, I mean, we use computers so much, but how really effective are we at using them? Because frankly, we weren't trained. We figured it out. But there's now quite a bit of training that is available online. I really like the software carpentry project. It's basically an organization that's been funded by foundations primarily, and they're specifically targeted toward, as you can see here by the byline, helping scientists build better software for themselves, typically, right? Even the formulas that we put in Excel spreadsheets are really software. So how can we do that as best as possible? So software carpentry has an amazing set of free online video lectures, tons of episodes that are relatively short and digestible, and they also offer free boot camps. The boot camps are 16-hour courses. The episodes, actually, if you go online, you can probably string together 40-plus hours of instruction and hands-on exercises. So that's one place to go, but there are many other places to learn how to code. Most of them are geared toward slightly different audiences, whereas software carpentry is specifically geared toward graduate students, postdocs, and faculty who are doing scientific research. So they understand the time constraints and also the rather specific needs. What language? There are a whole pile of languages. Python is my current favorite. R, MATLAB. But what really matters the most, I think, is that you have colleagues that can help you, or you can start a study group, and so that you have basically a support network to ask questions of, et cetera. All our Python and MATLAB all, of course, have amazing online resources, and they're completely geared toward scientists. Python is a very broad language, I should point out, and there's a specific organization called scipy.org that really oversees the community of scientists that are using Python. So Python is such a widely capable language that it can be used from anything that one might ever need to program, from GUIs to web platforms, et cetera. And a lot of those code we can ignore, but scipy can help us get to exactly what we need. So it's really important also to become familiar with this concept of relational databases and the management system software that runs them. I would say that the concepts, for most of us, it's the concepts that are most important, and one could easily get started with desktop applications like Microsoft Access or Open, LibreOffice Base. If you start coding in Python or R, it's really easy to start interfacing that to SQLite. And then the larger, more enterprise class relational databases require a decent bit of skill, but I'll say that I was able to teach myself how to translate a bunch of data that I'd been managing in Access into MySQL in about a single 8-hour day. So it's not unattainable, but that said, to become a wizard at using these systems does require a bit more work, but not unattainable. And then learning simple SQL allows you to just understand the concepts of how one gets data in and out of relational database systems. And even if you're not writing the SQL yourself, you'll get a leg up on talking to your data manager or someone that you're working with to pull the data out you need. You can basically write out your query in English if you understand the relational logic that is built into SQL. Or you can use, what I did and still do, frankly, is I use one of these point-and-click query builders, such as those in Microsoft Access, and it will write a query for me, and then I'll cut and paste it into MATLAB or Python, and can run that query right out of the small code snippets that I've written. So last, and is this idea that it's really, I think, would benefit our scientific community to participate in the open source revolution. I think all of us, of course, use open source software. It's become so ubiquitous that it's hard to avoid. But when I say participate, I actually mean contribute. And learn from do more than just learn about the software. And one of the, I think, primary contributions of the open source software movement is actually developing the skills, wisdom, and tools, as I write here, for massive effective collaboration, right? I mean, the community of people who are developing Linux, the primary operating system of the internet, is tens of thousands of people, and somehow that can be managed effectively. So how do they do that? We're being asked by NSF and others to collaborate and to have teams, and a lot of us aren't really that good at it, frankly. It's really challenging to do. So there are a lot of lessons that can be learned from figuring out, well, how do they do it in the open source world? Was Firefox written, or Python, which is completely also open source, or R? So contributing and learning how to contribute, I think, is one way to learn through practice, how to collaborate. And I think what I've seen is that it's enhancing my ability to collaborate on scientific efforts. My gateway drug to participating in the open source world was actually through electronics, and we were pondering at our CZO early on how we were going to have this high spatial resolution sensor network, when just to put in a capable data logging and data communication system was going to cost us thousands of dollars per station. And we realized early on that there was actually an open source hardware movement that was burgeoning around the Arduino electronics platform. So we played around. This is actually a schematic from one of our earlier models, and realized that we could do a lot of what Campbell Scientific Data Logger can do through plug-and-play open source electronics. And this Arduino platform is kind of at the heart of what they call the maker community, or which is exemplified here by this cover of Make magazine. And it's really unbelievably capable. And I would encourage you to all think about what you can do with in a weekend or that span of time with some of these electronics. It's really stunning. So I'm going to show you just a few examples. You know, the electronics boards are inexpensive, $20, $30 a piece. They have very standardized interfaces, and they are designed to be, as I say here, extended and copied and reused. And so a different company can make a compatible board using that's completely compatible with the software and also with the extension modules, which you can just snap together like Legos. So there are communities of people who get together to build things. This maker community, there are a lot of people out there. A lot of them are hobbyists, just playing around. Some of them are kind of at the heart of this this kind of revitalization of American industry and manufacturing. So we take these parts, put them together, and attach them to relatively low-cost commercial, what I call bare wire sensors that have no, sometimes they have A to D converters built into them, but they don't really have much in the way of data logging capabilities, so they're very inexpensive. Oh, well, that's not good. Missed a page there. So we've deployed them all over the place for a variety of uses, from soils to streams, and we have them logging high-resolution data in a variety of environments. We've even built devices like this dial-a-pump, where we can trigger the filling of 55-gallon, 200-liter barrels for suspended sediment geochemistry from a cell phone, from the comfort of your bed during a typical thunderstorm that peaks at midnight or 2 a.m. We've even developed complete laboratory instrumentation based on what this is that it basically measures the CO2 accumulation in these incubations of soil incubations within jars. We have this whole suite of 120 solenoids that are completely controlled by an Arduino that switches the loop for one jar through this Lycor gas analyzer for 6 minutes. We measure the slope of the carbon dioxide concentration as a function of time and get an instantaneous rate, or a nearly instantaneous rate. And we can cycle through 60 jars 3 times per 24-hour period. And we built this entire thing with about $2,000 worth of hardware, in addition to the $3,000 Lycor analyzer. So, I mean, what it does is that it opens up our capabilities as a scientist, but we can't all put in the R&D time, so we need to share. And that's where our team has recently been contributing back and sharing, and we're just really getting up to speed on that. So the best place to do that is GitHub. I actually just copied and paste off of the About page from GitHub, but so it may seem a little bit like a sales pitch here, and I guess it is. But GitHub takes version control, which is an absolute requirement for anybody who's doing software engineering. Whereas most of us have probably never used it. It's like track changes, but for a whole file system of text files related to software development. And it's amazing track changes because you can have comments and conversations about every single granular level change or large-scale changes, and you can have multiple versions simultaneously running, and it's almost like magic. And so every software engineer in the world has been couldn't imagine doing a single thing without version control running for more than the last decade, and yet we've hardly used it at all. So Git itself is command line version control that's very powerful. And GitHub has built a whole social network about sharing, Facebook style, around sharing work on code and other blueprints. So it's an amazing site. and it's expanding, and they're doing more than just sharing code. They literally are sharing the schematics to electronic hardware. So there are geeks that are out there that are planning weddings using GitHub because it's really very good at that. So the first thing you do when you log into GitHub, it actually asks you, well, what is your open source license? And that can kind of be a scary question because I think most of us think open source just means you give stuff away for free, but that's actually not true. An open source license is actually a type of copyright license that is used for computer software and the blueprints and design details of other products other than software, such as electronics. So, so it's an open source software that doesn't, or it's a copyright that doesn't reserve all the rights. Fundamentally, it releases the right for others to use, modify what you have, and then it reserves a few other rights. So choosing an open source license is actually an important decision. It offers way more protection than what we typically do, which is just post stuff on our websites. Oh, you know, take this. An open source license requires that whoever does take it give you, basically cite your work and give you attribution for that work. And as I said, it's also a legal document that reserves other rights. There are a whole pile of open source licenses. There aren't just one. Here's a list of them. You can see that there are 3 or 4 that are most commonly used, and each of these reserves different sets of rights. You can kind of group them into 3 or 4 main groups that are based on kind of how liberal they are versus how open they are. Public domain has no protections for even citing what you do. So if you just put something on your website without a license, you have no protection. And frankly, very little software these days releases public domain. Apache, Berkeley Software Distribution, or the MIT licenses require attribution, but allows commercial users to take the code and bury it inside proprietary software. The benefit is that suddenly your open source project has the interest of commercial users, and often they're very good contributors of ideas and other things because they see the value in it. They're going to use it for their own purpose, but you know, if they've added something to the base, why not share it back? And they often do. The new public license and the lesser new public license really are what's called copyleft licenses. They require that any derivative use the exact same license as them, and so basically it locks in any derivative of the intellectual property that's contained there into being open source in perpetuity. So so there's some choices to make, and there are good reasons, and you can read about them, but be aware of them and choose a license. Don't punt on it and just throw it into the public domain because you might not get cited for it. Related to open source software license are Creative Commons copyrights, and they're really more about documents, not blueprints, and you'll notice Creative Commons copyrights at the bottom of every Wikipedia page, and you will increasingly notice them at the bottom of every public data set. Because it is really the recommendation that data sets that are released to the public in repositories be given a Creative Commons license. Again, it's a protection for attribution. Every single one of these licenses requires attribution. So I guess this is just an example of the fact that these licenses, especially the Creative Commons, copyright, and these software licenses, have gone through very thorough legal review. Why make your own data use agreement when you can just adopt Creative Commons? It doesn't make any sense to start from scratch. Are you going to hire mountains of lawyers to check it out and run it through a bunch of court cases? Creative Commons has done that. So don't be afraid of those. So this is actually my last slide. I hope this has been useful to you for me to describe kind of my journey from being a data user and a data producer to really thinking more carefully about how I share my data and how others might share their data. So I'm open for questions, I guess, via text or other means. I'll let Emily moderate, I guess.
Sure. Well, thank you so much, Anthony, for giving your presentation, and thank you, everyone, for sticking with us while we get the technical difficulties sorted out. So at this time, if you have a question for Anthony, you can go ahead and type it into the chat box, and then I'll read that back over to you, Anthony, and that way we kind of have a record of the questions.
Excellent.
I see some typing happening, so we'll just wait a couple minutes for the questions to come in. And there's a question from Fox that says, Anthony, what's your GitHub username? I'd like to look at your repository.
Okay. Well, I will be very honest that I have only begun playing around with stuff on my particular repository, but I do have lots of repositories, so it'd be fun for you to look at. Let me get that up here. All right. So I only got started using GitHub a year ago, and we started doing it with the Observations Data Model 2 team, and I'm actually quite proud of what that team, which is led by Jeff Horsborough at Utah State University, what we've been able to do using GitHub. It's been quite amazing. So those pages are probably much more developed than anything that I have personally. Yeah, you're welcome to look around. I've got a bunch of stuff up. These are kind of the, oh, not just that one, sorry. So I'm pasting these in. We created a Stround Center organization. Well, the Stround Center organization has in it a bunch of kind of placeholder repositories, 3 to be exact. The one that actually is getting the most use is an Arduino software library for SDI-12 communication between Arduinos and smart environmental sensors. That was a pretty exciting development because so many environmental sensors are either analog or SDI-12. They don't really use the more common data communication protocols that are built into Arduinos. So we have a lot of people already adopting that. It's only been out for a year. But we also are trying to really move all of our open source electronics development work onto GitHub, and that process is just starting. We have just created, although it's not formally released, the Enviro DIY online community website, which we hope will be a place for people to do forums and microblogs around do-it-yourself environmental monitoring and science. If you click on that link, you will end up with a coming soon page, and we hope to actually have that release in less than a month. Actually, we're targeting November 14th, which is the first day of the next Public Lab barn raising, which we'll be attending. If you haven't heard of Public Lab, that's a pretty exciting group of people developing all sorts of do-it-yourself science projects.
Excellent. Any further questions for Anthony?
All right.
All right, it looks like it's quiet in the chat box. So again, Anthony, thank you so much for participating in our virtual workshop and giving a presentation today. I encourage everyone to check out our virtual poster session next Thursday. Again, that's going to be October 30th from 12 to 2 p.m. We have 8 posters and 2 vendors that will be participating. And I'm going to post the posters up to the Quasi website today or tomorrow. So you'll be able to take a look at the presentations that you'll be able to see during the poster session. So again, thank you very much for being here, and thank you, Anthony.
You're welcome. Thank you all for attending and for inviting me.